To the Verilog HDL subject. So today we will see with means modules and ports. So which is the second chapter in module 2. Okay. So after seeing the basic concepts in module 2, okay. So the basic concepts that is with respect to the lexical conventions, the data types, the system tasks and compiler directives. Okay. So after seeing all these the prerequisites, okay, to write the HDL code. So after seeing all these data types, conventions, and some library functions like the system tasks and compiler directives. So after knowing all those things, so now we'll move on to the modules and the ports here. Okay. So basically, so what is the module? Okay. So module is the one. So whatever now we are talking about means, as we are saying, we are talking about Verilog HDL. Okay. So Verilog is the language. Okay. So which will describe the hardware. So that is the Verilog HDL. Okay. So now to write, so in the C language, as all of you know, the C language will start with means hash include, okay, the stu.h, and if any other header files are there, after including that, okay, the void, so we call as main. Okay. So main function. So then we will write the code. So this is what the syntax, what we have, what we know with respect to C language. Okay. But if you come to the Verilog, so the Verilog coding will start from the module, will start from the keyword module. Okay. The coding will start with a keyword called as a module. Okay. So if there is a module, then there must be, at the end of the code, we will use end module. Okay. The keyword module and the keyword end module. So in between that we need to write the code. Okay. It will start with a module and it will end with the end module. Both are keywords. Okay. In between that we need to write the code. So whatever the different the abstraction levels, so like data flow, behavioral, switch level. Okay. So yeah, switch gate level. Okay. So all these that the gate level, data flow, behavioral, okay, and switch level. So any one of that modelings we can use to write the logic. Okay. So this is what we call as the module is a keyword which will use to start with the beginning of the code. Okay. And ports. Okay. Ports in the sense, so as the name suggests, so we will call as the computer or any device will have different ports. Okay. The USB port or parallel port, serial port, all those things. So that is nothing but we call as IO, that is inputs and outputs. Okay. The inputs and outputs we will define with the ports, so that we call as ports. So module means the keyword, means the module means it is a program. Okay. The Verilog program in short means that we call as a module. So in turn, the module we are using in the code as a keyword as the beginning of the code. Okay. So this is just it is the module and ports. Okay. Let us see what are modules and how we can use in the code. So now the module, so as I said, the module is nothing but a program, Verilog code. So that consists of the different components. Okay. We have here different components. So as we are seeing, this is one component. Okay. So component part means this is one of the component, this is second, 3, 4, 5, 6. Okay. So here these are different basically these we call as components of the module. Okay. This is module, start module, and this is end module. Okay. The module statement and end module statement, in between that it has different components. Okay. So that we will see now. Okay. So what are the different components of the module? Okay. So the module will start with the module name. Okay. The module name and port list means, okay, port list means what are the inputs and outputs. Okay. Then port declaration. Okay. So as I said earlier, it will start with module. Okay. The keyword module. After that module name. Okay. We will see in detail later. Okay. Module, and next we need to write module name, for example half header or anything user defined name. Then after that the port list, what are the inputs and outputs for the this particular module. Okay, so now the same thing here, the module name. Okay, it has the module will have the module name, then port list, then port declaration. So declarations in the sense, so whatever the port list consists of inputs and outputs, in that what are the inputs and what are the outputs and what is the size of those variables. Okay, size of the inputs and outputs, so that we call as the port declaration. Okay, so then parameters. Okay, so parameters, as we have seen in the lexical conventions. Okay, so parameters is, okay, is nothing but defining the constants. Okay, parameter a, parameter space a, then 30. So wherever a will be using, so that will be replaced with 30. Okay, so this is constants. Okay, the parameter is a constant, declaration of inputs and outputs, naming of inputs and outputs, then module name. So these all things we call as a first part of the first portion of the module. After that, okay, then declaration of wires, registers and other variables. Okay, so what are the inputs and outputs are there, that we will declare here in this portion. At the beginning we will declare what are the inputs and outputs and size of that. After that, okay, or even in the same place, we must declare what is the data type of that. Is it wire, is it reg? Okay, so is it a variable or is it a signal? Okay, or is it the constant? Okay, so all those things we need to declare with the proper data types, the register data type or the wire data type. Okay, so after declaring that, as I said, the 4 different abstraction levels we can write the code. So data flow statements. Okay, if we have the Boolean equations, okay, the problem we can define in the form of, means before the code we need to have the inputs, the design inputs. Either it can be the Boolean equation in the form of Boolean equation, okay, or in the form of truth table, okay, or in the form of the schematic, means the logic circuit, schematic or the logic circuit. Okay, or we can call as algorithm. Okay, algorithm, truth table, the Boolean equation, schematic. Okay, in any of the form we must define the design. Okay, so after defining all those things we can write the code. So one of the ways by using Boolean equation and by using assign statement. Assign is again a keyword. Okay, by using assign statements we can write the code. It means the module can contain this part of, means like this we can write the code. Or okay, so and it also can have instantiation of the lower level modules. So already we have seen what we mean by instantiation. Okay, so instantiation means the calling the function. Okay, calling the function. So what is the method of calling? So we need to write the module name and instant name, module name, instant name, and the inputs and outputs in proper order. Okay, inputs and outputs in a proper order, means we can call as port list in proper order. Okay, this is instance name. Okay, and this is module name. So like this we can instantiate the lower modules in the main module. So this is also one of the part of the, means it is one of the component of module. The next one, suppose we have truth table. Okay, suppose I have the design which has truth table. So by using truth table, okay, by the help of truth table, by using always and initial blocks. Okay, these all things we'll see in detail. Okay, so always and initial, again the keywords, by using that we can write the code if we have the truth table, the design in the form of truth table. Okay, so that is one of the component in the module if I write. Then the next one, the tasks and functions. So already we have seen like dollar monitor. Okay, so dollar stop. Okay, and dollar what is it, dollar finish. Okay, so that the system tasks if you are using anything. Okay, and the different user, it may be different user defined functions. Okay, even that function. Okay, so system task and functions, so that may be the one of the component in the module. The last one, after writing this is we call as a logic part. Okay, so always in the coding, so this is the beginning, this is declaration or initialization, and this is the logic. So this we call as, in general we can call as initialization, and this is we call as logic part, and this is end. Okay, this is end, initialization, logic part, and the end of the program. Okay, in the logic parts itself, the declaration in one of the four abstraction, one any one of the what is that method we can use to write the coding. This is behavioral, this is instantiation, this is using the functions. Okay, so all these things are we call as the different, the components of the module. Okay, the different components of the module. Okay, so next we will see by taking one example. Okay, so each one how we can write for one module, means one example. Okay, so that we can see. So this is these are the components of module. Okay, the next one. Okay, so let us take one example. So here we are taking the example. Okay, the SR latch. Okay, so basically, so what is a latch? So latch is the one which will store the, means for example 1 bit latch means it will store the 1 bit value, 1 bit binary value it will store, either it can be 0 or 1. Okay, so this is a SR latch, the logic circuit or logic diagram. Okay, the logic circuit of SR latch. So here we have the whatever dotted lines. Okay, whatever dotted lines, just to take as the black box, don't see inside. So let us concentrate on what are inputs and outputs, means ports. S bar is one signal, R bar is one, Q is one, Q bar is one, means there are two inputs and two outputs. Okay, so now as we are seeing in the design block, so here it will start. Okay, SR latch module. So module is a keyword, as I said, the code will start with the keyword module. This is a module, it must we need to write. Then SR underscore latch is a module name. SR underscore latch is module name. Then this is a port list. So as I said earlier, okay, if you see the black box now, two inputs, two outputs. Okay, and one more thing, yeah, okay, two outputs here and two inputs. Okay, the two outputs and two inputs. Okay, at this place you can write in any order, for example first input, second outputs, so like that. But during the instantiation, first left side in the bracket, always we should start with the outputs. Okay, so as we are seeing here, the SR latch is module name, and this is a keyword, and this is a port list. Okay, this we call as port list, two inputs, two outputs. After writing the port list, module name and module, here the port declaration. Okay, so how to declare the inputs and outputs? So in that, as we know, Q and Q bar are output, so output Q comma Q bar. So as the Q and Q bar both are of same size, means both are 1 bit, so because of that I can write in a single line, means output is a keyword. Okay, so we should not use outputs, always you should use output only. Output we have written Q comma Q bar. Okay, so as I say, both are the size is same, I can write with a comma after the output. Okay, suppose if size is different, then I need to use one more output line. Similarly, the input here. Okay, okay, similarly input is a keyword, and S bar, R bar is a inputs here. So this is the declaration. Okay, port declaration, and this is port list. Okay, so after the port declaration and port list, we need to write the code now, means logic part. Okay, so now we need to see the inside. So what is the input here? As I say, this design can be the Boolean equation, design can be what is that, algorithm, truth table, Boolean equation, so whatever the form. Okay, so we have the logic circuit form. Okay, we are seeing two gates here. Okay, so we are seeing two NAND gates. So directly we can use the structural modeling or gate level modeling. Means we can, this is the dotted line is a top module, means okay, this is the top module inside. Okay, so this is what we call as SR latch overall block. In that we are seeing two components called as, one is N1 NAND gate. Okay, actually one more, it should be N2 here, the name of the component. One is N1, one more is N2. So that we need to instantiate, that we need to call. Okay, in that case, as the NAND gate, so directly it is NAND gate only, so we can directly use the keyword as NAND. For NAND gate we will use the keyword as NAND. So write the NAND, okay, the keyword directly NAND. N1 is instance name, and what are the inputs and outputs with respect to NAND 1. First we need to write output. Output is Q, write first, then S bar, and what is one more input? Input is Q bar here, it is connected back, so S bar and Q bar. So this is with respect to the first NAND gate. If you take the second, again use the keyword same as NAND, because this is also NAND gate. Keyword you use same NAND gate, but instance name is different here, N2, and here output is Q bar and inputs are R bar and Q. So R bar and Q. So now this type of modeling we call as structural modeling, or we can call as gate modeling. Okay, means we are using the directly the logic circuit to write the code. Okay, and we are using the library functions, the NAND. Suppose if it is AND gate, okay, then we can use AND. Okay, suppose if it is OR gate, we can use OR. If it is XOR, we can use XOR. Okay, so like that the library functions directly we can use. So this is the logic part is over, declaration is over, and port list is over. Then whatever components, so both we have covered. Okay, and even connections. Okay, so this is a complete code for SR latch, that we call as design block. Then after that end module is compulsory, and this is module anyway, we will start with that. Okay, so this type of modeling we call as gate level modeling, and we have written this we call as the design block. Okay, this we call as design block for SR latch. Okay, so this is we call as the coding with respect to Verilog in a structural modeling with respect to SR latch. Okay, okay, this is how we need to write the code. Okay, so we need to understand here, start with module name, port list, declaration, logic part depending upon the input, what input type of the input we have, then end module. Okay, so after seeing this, the next is stimulus. Means as I told, this design block is the whatever our design, what we are representing in the language. To test that we need stimulus block. Okay, stimulus in the sense to give the inputs. For that we need to give the inputs to test the design block. How to give the inputs? So again we need to write the code to give the input. That block we call as a stimulus block. Okay, so in the stimulus block, okay, so module is the same here, module keyword, top is a name. Means this is how is, for example, this is SR latch and these are inputs. Okay, and these outputs will be connected here, and this module is top. Okay, this module is top. Okay, so top module, actually it is like this, you can see like this also, SR, and here is a top, SR, and here is a top, and this is inputs, and these are outputs. Okay, so like this. But externally, the top, externally it is not receiving any, it is not sending any signal, and it is not receiving any signal. Means top is a one module which don't have inputs and outputs. So but inside it is calling the, we are instantiating the SR latch, so that is having the signal that we can monitor as internal signal. Both inputs and outputs of SR latch as an internal signal for the top module. Okay, so because of that we don't have the port list for the top, we don't have port list for the top. Okay, but okay, so q bar, so uh, if you take the SR latch, okay, q bar as the outputs. Okay, but here in the top module it will means this is an internal thing. Okay, so that we are declaring as a input, sorry, wire, that we are declaring as a wire, so that we are declaring as wire. But if you take set and reset, set and reset are inputs for SR module. Okay, so input for SR module means, so if you take in this thing, okay, so there are two types of stimulus module we can see as we are seeing in components of the simulation. Okay, this is the top module will generate internally. Okay, what are the inputs for SR? Okay, if it is generating means that we should declare it as register. Okay, the top module generating the set and reset. Okay, that is S bar and Q bar, what we are saying, sorry, S bar and R bar, that is generated by the top module. So because of that we must declare it as register, whereas Q and Q bar are outputs of the SR module, so that is like input to the top. Okay, so that we will declare it as wire. Okay, so this is we will see how to declare it as wire and how to declare it as register. That's the next part in this module that we will see. At present the top module inputs q bar when you declared as wire, outputs as set reset, so that is as a reg. Okay, and here we are instantiating the SR latch, that is module name, instance name, and here first we need to write outputs, next we need to write the inputs q bar and set reset. Okay, then how to give the inputs? This is declaration, this is module name, this is declaration, and this is instantiation for which module we need to test, so that we need to call or instantiate. After that we need to give the inputs, generate the inputs for SR latch. What are the inputs? Set and reset. So here the set and reset that input generation will begin with initial and again begin and end. So as I told earlier also, the begin and end will be used wherever more than one statement I am using in the Verilog language, means I am using the statement. So all these things we call as a statements. If I am using more than one statement, then I can put begin and end. Okay, so I am putting begin and end here, and dollar monitor is used to see at what time what input I have given and what input I am given I need to, and what is output I want to see. So because of that I am using system task dollar monitor. Dollar time will give the current simulation time, and set value I am printing in binary, reset value I am printing in binary, and q output I am seeing in binary, and set reset. And so here the variable name, format. Okay, after that what variables I need to mention here. Okay, so this is to monitor the values I need to use the monitor keyword. Then so give the value, initially set equal to 0, reset equal to 0, both I am giving 0 0. After 5, this is a delay, after 5 nanosecond I am making reset as 1, again after 5 nanosecond making reset as 0, again after 5 nanosecond making set as 1. Okay, so how it will generate is, so if you write the vertical like this, set and reset here, initially both are 0, after 5 nanosecond the reset is becoming 1 and set is same, reset is becoming 1, and it will 1 up to 5, because after 5 again it is make it 0. Okay, and that will 0 for 5 nanosecond, again after 5 I am making set as 1, like this. So this is continuous. So delay is 5 nanosecond, 5 nanosecond, 5 nanosecond. Okay, so initially both are 0 0, after 5 nanosecond I am making reset as 1, after 5 nanosecond I am making reset as 0, after 5 nanosecond I am making set as 1. Okay, so this is how the signal will generate with respect to time. Okay, so after that, unless until the simulation stops, so the same values will be continuing further here. Okay, this is how we will generate the inputs by using the stimulus block. Okay, and the stimulus block components here, port list means module name, declaration, calling the design block, and give the generate the values for inputs of the design block. Okay, so this is with respect to the design, sorry, stimulus block. After seeing design block and stimulus block, okay, so this is how the sample code, how we need to write Verilog code for design block and stimulus block. Okay, the next one, okay, now we will need to see, now we have seen what is module and what are the components of the module, and with example we have seen what are the components. Okay, so now we will see what are ports. Okay, as I said earlier also, the ports are a one which will help to communicate with the, means communicate with other modules. Okay, one module with other module, okay, or one device with other device. Okay, so ports is nothing but inputs and outputs. So as this says here, the internals of the module. Okay, ports provide interface by which module can communicate with the environment, means different modules. Okay, but the internals of the modules are not visible to the environment, means as I say, if you take the black box like this, these are the inputs and this is the design block. Okay, the ports are not bothered with what logic we are using here, means the inputs and outputs will not bother the what logic we are using the inside. We can use data flow modeling, any modeling we can use. Okay, so that doesn't bother. Okay, and these ports also we can refer as terminals. Okay, as I said, now internals of the module can be changed without affecting the environment as long as interface is not modified, means as long as I change these inputs and outputs, okay, whatever the change I can do inside, that is not affect on the ports if I am using the same ports. Okay, so now this is what we call as, means what do you mean by ports? That is nothing but inputs and outputs. Just example, so what we are seeing here, so if there is any, the full adder, okay, the 4-bit full adder, means if there is a adder, okay, like 4-bit adder means, okay, this 4 bits and this 4 bits like A and B, and always sum will be, and again it will be 4 bits, that is we call as the 4-bit adder. Okay, see in 1 bit the carry you can take. Okay, the same thing here, the 4-bit full adder, so A will be 4 bits, B will be 4 bits, and C is anyway the carry is single bit, and sum is 4 bits and carry out is single bit. Okay, so this we call as ABC in and sum out we call as ports. We call as ports. Okay, the next, now the list of ports, as I said earlier, the list of ports, okay, means in the previous full adder we have 3 inputs and 2 outputs. Okay, the 3 inputs and 2 outputs. The list of ports will have only what are inputs and outputs, not the size here. Okay, and this is the module name and this is the keyword module, and there is means there is no rule that the module should have the ports only. So without port also we can declare. So as we declared in the stimulus block, module top no port list. Okay, that is also valid. Okay, so in stimulus block we will not use any ports there. Okay, so there is no port list. Okay, for previous full adder we have 2 outputs and 3 inputs. So this we call as the port list of port. Okay, then port declaration, as I said earlier, the port declaration for any module, okay, the variable or port, it can be input or it can be output or it can be input and output. So this is input, this is output, and this is bidirectional. Okay, So if you take the data bus of any processor or any device, okay, so it will be usually the bidirectional. If you take microcontroller or microprocessor, so bidirectional. Okay, so other ports, if you take a display, it is output only. Okay, if you take any keyboard, so it is input for the device. So like that, we can define the variables, okay, as input, output and inout. Okay, so input port, the keyword is input, and output port, keyword is output. Okay, for bidirectional it is in out, not input output. This is in out for bidirectional. Okay, if there are more number of inputs, it is nothing but not inputs, it is input only. Okay, that we need to keep in mind. So this is how we can declare the ports. Here is just example. Again, it is example of 4-bit full adder. Okay, 4-bit full adder. So now this is module name, 2 outputs and 3 inputs. Okay, and here we are declaring the size of that. Means in that output sum is of 4 bits. 4 bits means 3 down to 0 sum. What is the format here? Output keyword, then size of the variable, then sum. Okay, the variable name. Okay, after that semicolon. Okay, so here also we should write the semicolon. This is one statement, semicolon. This is one statement, semicolon. Okay, this is 4 bits. Similarly, output cout, we can see here sum is different statement and cout is different. Why different is the size of the sum is 4 bits, size of the cout is 1 bit. So because of that, we need to declare with the different statements. Similarly, AB is 4 bits, that is input, size of the inputs 3 down to 0, 4 bits, and A comma B, because A and B are of the same size. Where scene is the single bit, that we need to declare separately. Okay, so now we are talking about only the declaration, not the logic part. Okay, we have declared outputs here, we have declared inputs here with the size of the variable. Okay, similarly, if you take the flip flop, okay, Q is output, D is input, clock and reset are inputs. In that case, output Q, that is only if it is only single flip flop, single bit flip flop, then it is only 1 bit output Q, and input QD clock, all are single bit, so we can declare with a single line. Okay, even if you declared with input D, input clock, input reset, doesn't matter, both are same, but we need to give the individual statement as semicolon after writing. Okay, so this is how we can declare. Okay, as I said, this is not a full code here, logic part is not included. Okay, no logic part here, we are concentrating only on the declaration part. Okay, so this is how we need to declare the ports, inputs and outputs. Okay, so now okay, so now here just we are talking about we have seen how to declare the ports. Okay, with size, but what are the data types we have not mentioned here, whether is it wire, is it reg, we have not mentioned in this slide. Okay, for that, how to use data types, for that there is a rule in Verilog. Okay, so port connection, that we call as port connection rules. Okay, so in the port connection rules, so the port connection rules are this diagram we need to always keep in mind. Okay, so this diagram we need to keep in mind. So what it says is, okay, so what it says is, suppose we have one module, we need to write one module. Okay, or we are writing one module like half adder. Okay, half adder I am writing. For example, for this module I have some inputs like A and B, 2 inputs I have, and 2 outputs I have as sum and carry. Okay, what to declare inside the code? Inside the code, what I have to declare data type with respect to A and B, and what data type I need to declare with outputs S and C. How it will be is, okay, so this is the same box like half adder. Okay, whatever we are seeing, Okay, so whatever you are seeing inside names, okay, inside names, that is what we are using inside the design. Means, for example, a and b are the variable names. This is input for the module. Means, if there is a input, you can see the direction here. If there is a input for the module, then inside the module, okay, inside the module, those things I need to declare as inputs with the data type net. With a data type net. Means, while writing the half adder code, while declaring a and b, I need to declare those inputs as nets. How to declare, we'll see later. We need to see now what, how to, means what to declare, inputs what to declare. I need to declare as net. Suppose I have the outputs like this. I have the outputs what to declare in the module. Within the module, I need to declare as either register or net, anyone. Okay, I need to declare sum and carry as either register or net, anyone I can declare. Okay, suppose I have the bidirectional. Suppose not for half adder, somewhere I have the bidirectional. In that case, inside the module, I need to declare it as net. I need to declare it as net in node if it is in node. Got it? So now, whatever the module, if it has inputs, outputs or innodes, within that module, while writing the code, those inputs and inputs we need to declare as net. Outputs I can either declare as register or net depending upon coding, and bidirectional I need to declare as net. Okay, so this is with respect to what I need to write inside the code. Suppose, okay, I need to interface this particular half adder to the some other module, some other x module. I need to interface. Okay, I need to interface this module to the some other module. In that case, whatever the outputs of half adder, okay, half adder, outputs of half adder in this x module, I need to declare. How to declare? Okay, if it is output, the output is connected to some other, then we need to declare it as net in this module. Okay, suppose inputs are coming, means from this external module I am taking as input. In that case, what's I need to declare in this module? Okay, I need to declare it as register or net in this module. If I am receiving any inputs from some other module, in that module I should declare either register or net. If it is bidirectional, is connected to other module, even in inside or outside, I need to declare it as net. Okay, so if I am receiving the signal from other device, okay, in that device I am using as reg or net. It is similarly like the output, this signal will act as output for that. Okay, if any signal is acting output for one module, inside that I need to declare it as reg or net. It is same thing here. Okay, so these things we will it will be more clear when we are going to write the programs. At present, you just think in the module, while writing the code, inputs will declared with net, output inputs will declared with net, and output we can declare with reg or net. Okay, so this is what we need to keep in mind, and these are very important while declaring the inputs and outputs. Okay, so this is what the same thing here. The inputs, internally input ports must always be net, externally input can be connected with reg or net. So this portion, the same thing, instead of diagram, just is given in the text format. And outputs, internally it must be declared with reg or net, externally it must be connected as net. Okay, same thing here. And okay, similarly inouts, okay, inouts, internally it is net and externally also net here. Okay, as it is only 3 of the types, input ports or inouts, so the thing they have given. Okay, and one more thing, the width matching. Okay, it is legal to connect internal and external items of different sizes when making inter-module port connections. When you are connecting one module to other module, so whatever size of the ports, even if it is mismatched, so it is okay. Means it will give the warning, but it is not a wrong thing. Depending upon application, we can use. And the one more thing, unconnected ports. Okay, unconnected ports means here sum is there, ABC is there, COT is not there. Output port COT is not connected. Okay, means it is not means Verilog allows, means it is not error, so we can leave like this. Okay, if you don't internally, I want that is signal, internally I want to see. Okay, but externally I don't want to connect that signal to outside. In that case, I can leave like this. Okay, means Verilog supports the ports remain unconnected. So this is regarding the port connection rules. Okay, and how to declare the port declaration. Okay, and here the example of illegal port connection. Okay, so illegal port connection is here. So as we are saying, to illustrate port, assume port module is full adder module, full add 4 is module name is instantiated in the stimulus block. Means in the stimulus block, I am instantiating in the stimulus block top, I am instantiating the full add 4. Okay, so here I am declaring as AB as register. Okay, and sum is output here, and this is module name, instance name, and these are the port names. Here what is wrong here? What is wrong is, as I said here, okay, for stimulus block, okay, as I said, two things, one is design block and stimulus block. The output of this will act as input for here. Okay, and input for design block will act as output of stimulus block. Always the design blocks, okay, always the module inputs we need to module inputs we need to declare it as wire, and outputs we need to declare it as reg. Okay, so as I said, the design block outputs, that is sum and carry, we need to declare it as wire, because that is the input for stimulus block. We need to declare it as wire sum and wire cout. And what are the inputs of the design block that will act as outputs of the stimulus block, that we must declare as register. So that we have declared as correctly. But what is the wrong here? Sum is declared as register instead of wire, so that is a illegal here. Okay, the sum is declared as register instead of wire, so that is a illegal here, that is illegal port declaration. Okay, so as I said earlier, okay, if we have design block and stimulus, outputs of this will act as input for stimulus, and the input of design block will act as output of stimulus block. Okay, always input should be, in any block, input should be declared as wire and output should be declared as reg or wire, but usually we will declare as register. Okay, so the AB is input of design block, that we need to declare as output of stimulus declared as register, and sum and carry are outputs of design, and inputs of what is that, inputs of the stimulus, that we must declare as wire, and here it is declared as register, so that is a illegal here. Okay, so these all things, so at present, okay, at present no need to worry about these things. Okay, so as we go on writing the programs, it will be more clear while writing design block and stimulus block. Okay, so this is regarding modules and component of modules. Okay, and how to declare the ports, and what are the different types of ports, and what are the connection, how to declare the data types within the module, and how to declare the data types when you are connected to the different modules. Okay, so these all things we have seen. So in the next part, okay, so after saying all these things, so in the next part again we will see what is that, what are the, how to connect, how to instantiate the modules. Okay, what are the different types of that in the next class.